A question for you. Given a set S, what did we define the cardinality of S to be?
Unique values.
Say again?
Unique values.
What about the unique values?
In a finite.
You could, some of those words go in there. Roman?
I mean, that's kind of like in a set S.
In a set S. Seth? How many distinct elements do I have? As long as that number is finite. But really, what we're describing is a function. A function that counts the number of things in S. And depending on the way we want to do it, we could think of that function as having the domain 1 through n, or the domain of the entire natural numbers. Here's the first thing, the second thing, the third thing, and so on. This is not a finite set. Oh, okay. That changes things. If I really want to define cardinality properly, I need to know some things about the function that I'm taking from A to B. So I'm going to say two sets have the same cardinality if and only if there's a bijection. Wait a minute, what's a bijection again?
It's onto and 1 to 1.
From A to B. So not only do I have to be able to say, here's the first element, here's the second element, here's the third element, I have to do that in a 1 to 1 and onto fashion. I have to hit every element in S, and I have to do it uniquely. In this case, I hope that makes perfect sense. I could literally take my elements of S and write them like that, up to the last one, where F of I is SI, 1 less than or equal to I less than or equal to N. If you know the first thing, we'll call that F of 1. The second thing, we'll call that F of 2. That function is definitely 1 to 1. If S is finite, I've hit all of them. If I do this in a 1 to 1 fashion, let me ignore the onto part for the moment. If I have set A and set B, the map from A to B is 1 to 1, then I know the set B can't be any smaller than the set A. Because I could miss something in the set B. I didn't talk about onto, but I definitely hit in a one-to-one way. Then everything in A goes to different things in B. I can't lose size. So sometimes it's easier to try and figure out whether my function is just one-to-one. And then do this in two directions. If I make a function from A to B that's one-to-one, then I know the size of A is less than or equal to the size of B. If I make a function from B to A that's one-to-one, and I know the size of B is less than or equal to the size of A, to be less than or equal in both directions means you have to be equal. Like we did with subsets back in chapter 2, section 2. I can do this. I'm still bugged by this. That's infinite. Because there's no n that makes it to the last natural number. But I like to think of the natural numbers as the counting numbers. So I'm counting things. So let's consider a finite set or a set that has the same size as the natural numbers. These are called countable sets. But we have finite sets and we have countably infinite sets. Now, if I have a finite set, its size is the biggest number for the number of things in it. If I have 100 things, 1,000 things, 287,362,403 things, I don't care, I have a number, right? I need a label for something being countably infinite. So I need a name for this size. I don't just want to say infinity. So I'm going to invent a new symbol. I'm going to steal it from Hebrew. The size of the natural numbers is called Aleph. And it's Aleph 0, Aleph with a subscript 0, or Aleph null. Aleph is the first letter of the Hebrew alphabet. Aleph is a silent letter in Hebrew. So I'm going to say this size, the size of the natural numbers, called Aleph null.
What can you just say it's infinity?
Because there are different infinities. This is the first one. This is a countable infinity. Infinity is weird. Here's a question for you. Here are two sets. Which of these sets is bigger?
divided by 2?
I would hope that it is obvious that the second is a subset of the first, right? B is clearly a subset of A, and what's more, it's definitely not equal to, right? Remember this definition. I have a function from A to B, right? F of n is 2n. Two questions. Is this function one-to-one? Why do you say no, Emily?
Because their cardinality isn't the same.
I don't know that yet. I don't know that the cardinality is the same unless you can show me that this is not a bijection. So I'm trying to prove that these either are or are not the same size. If this function is one-to-one and onto, they're actually the same size. How do I show whether or not something is one-to-one? Chapter 2, section 3. The homework, I just get back to you.
Don't they have to have the same range?
A range is something in a function. A function has a range. I only have one function up there. So I can't have the same range when I'm only talking about one function. A function is one-to-one if different inputs go to different outputs, or when the outputs are the same, the inputs had to be the same. So I'll write that down again. If f is 1-to-1, then f of x1 equals f of x2 implies x1 equals x2. The only way to get the same output is to get the same input. So let's ask, is this function one-to-one? Suppose f of n1 equals f of n2. Suppose we have two numbers with the same output. Well, the definition of this function says that f of n1 is 2n1. And f of n2 is 2n2. I'm allowed to divide by 2, aren't I? This function absolutely is one-to-one. That's only half the battle. What's the other part? Not just one-to-one, it's also onto. How do I know if a function is onto? Page 153. To show that f is one-to-one. To show that f is onto. That was the hint dropping. Gee, I think something should go in your formula sheet. To show that something is onto, for every y in B, there's an A that hits it. Write that definition down. All y in B, there exists x in A, so f of x equals y. So pick a number in the set B. Let y be an element of B. What was our set B again? Set of even numbers. Y is an even natural number. Wait a minute. If it's an even number, how can I write it? 2k, where k is a natural number. Normally I'd say integer, right? But integers allow for negatives. Natural numbers only are non-negative. So I'm going to say natural number here. Hey, wait a minute. 2k, where k is an n, that's f of k. No matter what number you pick in the second set, whatever even number you pick, if I divide it by 2, I found the a that goes to it. Okay. Okay, wait a minute. This f is 1 to 1. This f is on 2. This f is a bijection. And that means the set A is actually the same size as the set B. There are just as many even numbers as there are numbers. Even though I took half of them away. Half of infinity is still infinity. And it's the exact same size. Somebody pick another number. Any number. 5. If I only look at multiples of 5, 0, 5, 10, 15, 20, 25, 30, and keep going, how many of those are there? The same size. My function, f of x, is 5x, not 2x. There are just as many multiples of 2 as there are multiples of 5, as there are multiples of 1. Even though there are clearly fewer numbers. I took a bunch away. Infinity minus however many you want, it's still infinite. This is why I said you needed aspirin for today. Questions?
Same with calculus whenever we're doing graphs to the limit of infinity. And how those functions can be the same, they have the same. If the slope. It would only be the bigger infinity if it's like squared.
Squares. Here's the problem. If I only allow non-negative numbers, that function is 1 to 1. No negatives, only 0 and positives. As a matter of fact, that function is strictly increasing, which makes it pass the horizontal line test. It's 1-to-1. More than that. For this set S, it's onto. There are just as many squares as there are even numbers, as there are regular numbers, as there are multiples of 5. Because I'm only looking at half the parabola, right? That's the 1-to-1 part. Why is it onto? Because all of these numbers are perfect squares. I'm not going to miss any of them, am I? As a matter of fact, I could even show that this is a bijection by writing out the set N and writing out the set S. There's the function f, isn't it? That's definitely 1-to-1. It's also definitely onto. You're not going to miss anything in the bottom row, even if you keep going.
Are we only going to be working with natural numbers as of right now?
Yes.
Okay.
More questions? I would like to invite you to stay at a hotel. David Hilbert's Infinite Hotel. The Hilbert Inn. Yes, it's a bad joke. Here's the deal. Hilbert has a hotel with Olive Mill rooms. Got countably infinite rooms. They're all full. I show up at Hilbert's hotel. And I say, hi, can you put me up for the night? And he says, yes. Why?
You're able to stay in somebody else's room.
Nope, one person per room. I'm not even gonna let you stay with your girlfriend. One person per room.
Infinity groups.
Yeah, but I can't walk out to the last room. Remember, they're all full. What room is he gonna put me in?
Tell everyone to just like go like down one room, and then it creates a space at the beginning.
Ho, 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 ho. All 15 of us show up. Can we all get our own room? You just put person in room 0 in room 15, and 0 through 14 are all available to us, aren't they? I can fit any number of people you want in this hotel, even though every room is currently full. Ready for the crazy idea? I bring countably infinitely many people to the hotel and say, hey, David, I got infinitely many people behind me. Can you put us all up? And he says, yes. How? Well, I can't just say the person in room 0 go infinitely far down, they never get to a room, right? I still need to put people in rooms. How do I make infinitely many rooms open up? Then nobody ever actually gets into a room, right? They keep shifting and shifting and shifting and shifting, and I never get stopped. I don't want that. I want everybody to eventually stop in a room. Again, then I never get to stop, right? The last person in my list doesn't get a room. I want to put them all in one room and each person in their own room at once.
Isn't it like, you tell them to like go to like a room that's like double the current room number that they're in?
Wait a second, didn't we just spend all this time showing that this set of rooms and this set of rooms is the same size? Notice that all of the odd rooms are now open, aren't they? If you live in room 1374, you're going to room 2738, 2748. If you live in room 0, you stay where you are. You live in room 1, you go to room 2. You live in room 2, you go to room 4. We left 1 open, we left 3 open. We're going to leave all the odd numbers open. And there are countably infinitely many of them. I'm telling you, man, infinity is weird. I need more numbers. I need more numbers. These are the natural numbers. Emily, you asked me a question. Are we only working with natural numbers? I'm going to throw that answer out the window now. I want to work with other sets. So let's work with the integers. Clearly there are more integers than there are natural numbers, right? No. Why? Here are the natural numbers. Here are the integers. I'm going to make a 1-to-1 and onto function. Somebody flip a coin for me. Positive or negative? So to count the integers, I go 0, 1, -1, 2, -2, 3, -3, 4, negative. And that's the first one, the second one, the third one, the fourth one, the fifth one. I put them in order. I count them. That's countably infinite. I need more functions. I need more numbers, more numbers, more numbers. I know. Let's look at all the possible positive fractions. All of them. That's got to be a bigger set. Nope. You've got to be kidding me. I'm going to play the same game. I want to line up all the fractions in the right order so I can count them. How do I arrange the fractions? I'm going to make a giant table of fractions. If I continue all of these columns infinitely down, and I continue each row infinitely off to the right, you agree with me that we get all the fractions that are positive? Every positive possible fraction will show up somewhere. Integer on top, integer on bottom, somewhere on this list. I need again a coin flip. Right or down? Down. So I'm going to start at 1. That's the first number in my list. You said down. So I'm going to go down first. This is the second number in my list. But now I'm going to go diagonal. That's the third number in my list. That's the fourth number in my list. And I'm going to go back diagonally. Wait, when I hit this number, that's 1 again, isn't it? That's 1 again, skip it. That's the next number. That's the next number. Wait a minute, I already hit that number, right? That's 1/2. I already hit that number. That's 1. I already hit that number. That's 2. So I skip all of these and I end up at 5 down here. And I go back and forth diagonally. Will I eventually hit every fraction? Will I miss any? This math is 1 to 1 because when I ran into a number that I'd already seen before, I skipped it. It's 1 to 1, it's on 2, that's a bijection. Point. In my investigation into infinity, I reached the question, okay, so everything's countable. Along comes my buddy George Cantor, and he says, no, here is an uncountable set. The numbers between 0 and 1, the real numbers between 0 and 1 are not countable. Now here's the problem. The following proof is a proof by contradiction. This is an important proof by contradiction because what it really tells me is something foundational about the way we do math. If it's by contradiction, we start by saying, suppose the set from 0 to 1 is countable. Then there's a first number in my list. Whatever that number is, it's a real number between 0 and 1. R1, this is f of 1. The first number. Oh, R0, right. Start, my natural number start at 0. Good catch. F of 0. What do I know about this number? It's between 0 and 1, so its decimal starts 0 point something. Every number in the decimal expansion is a digit between 0 and 9. So I will have the first digit. Oh, wait a minute. This is the first digit of the 0th number. I'm going to give it a double subscript. The second digit of the 0th number. The third digit of the 0th number. There's just one restriction. The tail can't be 9s forever. Because if it's nines forever, technically you're rounding up. So we can't end with a bunch of nines. But that's just R0. There's R1 and R2 and R3 and R4, right? Because this is countable. So there'll be an F of 1. And an F of 2. And so on. You with me so far? This list goes on through all the natural numbers, right? I'm going to make a new number. Where D star I, the ith digit of this number, comes from going to Ri minus 1, taking the ith digit, and adding 1. But if it's a 9, don't add 1, just go to 0. So I am building a brand new number. The first digit in this number is 1 bigger than this. The second digit in this number is 1 bigger than this. The third digit is 1 bigger than this. The fourth digit is 1 bigger than this. What's the problem with R star?
One to it. Which decimal place do you need?
Oh, yeah, in the ith decimal place. I add 1 to the digit in that spot. So if you had 0.235, I'd go, the first number was 0.235, then in R star, the first digit is a 3, 0.3. Go to the second line, that number is 278. Take the 7, make R star 3, 8. I'm going to build R star by looking at my list. It's going to be different in every single row on the list, isn't it? R star is not on the list of F of I. I hope whatever that is, it's calm, but it's going by. What does that mean about my function? My function F. I have a real number that's not in the output. It's not on to. We made a function that we said was a bijection. Because we said this function was, this set was countable. If it's countable, F has to be a bijection, and you've just shown this function is not on to. That's my contradiction. It's a contradiction because it contradicts being countable. Countable requires this function to be one-to-one and onto. Now you may be saying, okay, well, maybe this function, f that you picked, did I ever tell you what f was? That means that any function that you pick is going to fail to be onto. And if any function fails, then every function fails. F is not. F is never onto, no matter what function you pick. And that means this set cannot be counted. But wait, there's more. The set contains a countable subset, right? I didn't say anything about F not being one-to-one. And that means that the size of this set is bigger than the size of the natural number. And this is why I couldn't just say infinity set, because this infinity is smaller than this infinity. Uncountably infinite sets are bigger than countably infinite sets. I need a name for this size. I'm going to steal again directly from George Cantor, and I'm going to call this a continuous set. It's a continuum. It's all the real numbers. It's a solid line. The continuum C. That's the size of an uncountable set. However, when Cantor wrote this argument, a bunch of people got really, really pissed off. Well, think about it. The way I made R star was to pick an infinitely collected set at once. I made infinitely many choices. I looked at the first digit in the first line, second digit in the second line, third in the third line, fourth in the fourth line. It's called a diagonal argument, because we look at the diagonal of this giant list, but that's infinitely many numbers, and I was able to say, no, I'm going to pick something different infinitely many times at once. That argument pissed off a lot of people in set theory who said, no, you have to be able to explicitly build this function. And you can't explicitly build it infinitely often. That takes a finite amount of time each step. Remember Zeno's paradox? In order for something to move, it's first got to go halfway, and then it's got to go halfway, and it's got to go halfway. It never actually moves anywhere. All motion is illusory. Well, I'm sorry, you arrived at this classroom, you moved. So Zeno's wrong. And Cantor appealed to that. And he said, just as motion is real, the ability to do a continuous thing is real. So there are at least two different infinities. All of zero and the continuum.
Did you do that in between 1 and 2?
Same size.
Okay.
Just add
Just
one.
make sure.
Think about it. If I go from 0 to 1, then I go from 1 to 2 by making the first digit a 1. And as a matter of fact, any bijection works, right? You're going to love this one. Set A is the set from 0 to 1. Set B is the set from 1 to infinity. f of x equals 1 over x. That's 1 to 1 and on to. There are as many numbers between 0 and 1 as there are between 1 and infinity. Infinity is fucking weird, man. I can actually show that any interval from A to B is the same cardinality as the continuum. If we think of this like a piece of a line, right? From 0 to 1, from 0 to 1, that's a line. Yes? 0 to 1, right? That's a line segment. Now pick another line segment. Any length you want, any numbers you want. Here's my function. To map the first line to the second line, start at this point P and draw from P to any point between 0 and 1. All you need is a ruler. Aren't you eventually going to spread this entire line onto this entire line? Every interval is the same size. I don't care if you're going from 0 to 1 or from 1/100th to 2/100ths. There's the same number of numbers in there. Two things. This is called the Schroeder-Bernstein theorem, but I hope it makes sense, right? How do you show A is less than B? You show a function that's 1 to 1. How do you show B is less than A? You show a function that's 1 to 1. They just don't have to be onto anymore. This proof actually is fairly recent, only about 130 years old. So this is new ideas in mathematics. Cantor's argument itself is less than 200 years old. All of these developments in set theory are modern, but they're all related to computability. Whether or not you can actually compute something is based on the countability of the program you use to do it. Page 175 talks about uncomputable functions. But in order to talk about uncomputable functions, I need to talk about how functions work. I got to do algorithms. This is your introduction to what will be CS 341, algorithms analysis. I'm going to do the baby version of it. We'll start that on Wednesday. Please note, I said there were at least two infinities. Alice sub 0 and the continuum. When you take the collection of subsets, you get a bigger set, power set, right? What if you take the power set of something that's countably infinite? No one currently knows whether or not that number is the same as the continuum, or if it's some other infinity in the middle. So there could be more infinities. I've only shown you 2 of them. We'll start algorithms on Wednesday. I will see you all then. A reminder that chapter 2, section 4 is due on that day.